So we'll continue with conservation of momentum today, and it's a bit of a deja vu all over again of what we did for conservation of mass. You remember that for conservation of mass we talked about moving reference frames kind of matter, and we elicited this idea of a static pipe, a jet engine, and a balloon as conditions, if you like, for a static frame of reference, non-moving, a pipe, cut off, flow in, flow out. For a jet engine was really for a moving but non-deforming, stays the same size but translates, and a deforming control volume, which was the balloon. And so we did that for conservation of mass, and so we can now do that for conservation of momentum. And it's not an esoteric exercise in that it's useful to us because it allows us to be able to characterize these systems. So even though this guy here, I think it is a guy, is moving in this, we can treat this as our first one, as a static system to be able to define behavior. And so that's my plan for that. So this is the pipe, if you like. This is a Pelton wheel. You'll get the idea of the fact it's an old mill, but these are used in power plants, hydroelectric plants. And all it is, you can't see the business end of this, but all these are a bunch of cups that are moving around. There must be a jet going from right to left below the axis of this, which is shooting it so it goes around. And so those are converting the kinetic energy of the jet into the rotational energy of this wheel, which of course you can use to grind corn or run a sawmill. It may be in this case, it looks like there's a sawmill on the, a saw blade on the back, or you could run a generator off this. There's another one that came up here, which is a really cool one, where a guy uses a washing machine engine to be able to run water from his house in New Zealand uphill, down a pipe, into the washing machine, turn the motor backwards, which is also a generator. A motor and generator just run in reverse, and generate electricity for his house. I won't show you that one because he made me take it down. He filed a strike against me on YouTube, so I can't really do that, but I guess if you're that interested, you can look at it. So the Pelton wheel is a case of a moving frame of reference. You could think of it as going in rotation. We'll talk about rotation tomorrow, Friday. But you could also think about it just pushing a vane along, and there's an example in the book, which we'll draw from, which does that. And finally, the third thing that you saw last time as well, and that is the sleeping giant, as it's referred to. And that is the idea that you can have, well, if it runs, you can have the idea of a decapitated gas cylinder. And of course that's a moving, not really deforming, but it's changing in volume. And so it's a bit like a balloon, right? Balloon shrinks as it buzzes around the room as you release it. This is flying around the room or across the room. It's not shrinking, but certainly the pressure inside is decreasing as the mass inside is diminishing. So it's not steady inside. And so we'll talk about this as our balloon analog. So those are the three analogs that we'll talk about. And so that's my plan for today. And we'll build on what we have already. If I can get this thing open, okay? So that's the plan. So I'll just get started here. So this is our correct day of where we are. These are the three examples. I won't recap this right here, but I'll do it somewhere a little bit differently. So we talked last time about this. This is already done. We talked about the undershot weir. And I guess the message from that is that if you have the gate down, there's a pressure on the gate. If the gate is up, the force that's applied on the gate, not obviously, but perhaps after the fact, after we've done the analysis, it makes sense. The force on the gate is less if you don't have it all the way down, if you have water flowing underneath it. I guess in the limit, if you took it up all to the surface so that there was only a slither of water catching the back of the weir's pressure, then the force on the weir would be very small. So it makes perfect sense that as you raise the weir, the reaction force that you apply is less. The three cases we'll look at are, well, let's name them this way. The jetpack, jet rev, static. So this is going to be static and non-deforming. This is our pipe, if we remember. The vane is moving and non-deforming. And the third one is the decapitated cylinder, which is moving. It's not really deforming per se, right? But it is changing in mass. So this is kind of the analog to deforming, if you like. So pipe, jet engine, balloon. So that's the plan. So just to recap what we have to put everything in the same place. Let's do that. Let me make the screen a bit bigger. And so let's talk about each of these two systems that we've talked about. And the systems are this. We have a control volume. That control volume can potentially move at some velocity. We have velocity in. We have velocity out. We've talked about a normal to the boundary direction. We've talked about applying a force. Let's talk about applying a force to that volume. And defining the different behaviors. We define a coordinate system, X and Z. And what else do we need to do? Well, that's probably enough for now. We can define two expressions. So conservation of mass. In shorthand, it's written as the density times the rate of change of volume plus the volume times the rate of change of density plus the sum of the mass flow rates is equal to 0. The mass flow rate here, and for the other case, is going to be what we call the relative to the boundary velocity, the area, and the density. So that's important, that this is relative to the boundary velocity. You'll remember that we described that in terms of my sailboat analog, not really a sailboat. And let's draw a tower on it instead of the thing. And that is that if this boat is moving at some velocity VCS, is squirting out water at some velocity W, then relative to an observer, it looks like this, the velocity static. So V static is equal to control surface plus the squirting velocity. So that's so this is this velocity here. So that's important. And if we look at momentum, I'll write it in shorthand. V for velocity, not for volume. Then this is merely written as the sum of the forces, say in the x direction, is equal to the velocity in the x direction multiplied by the mass rate. These are both summations. So I draw that here because this mass rate here is also in terms of relative to the boundary velocity. So it's whether it's going in or out, that's what we care about, right? If you're going at 400 miles an hour and water's trickling out of your front at 1 meter a second and coming into the back at 1 meter a second, you only care about that 1 meter a second. It's irrelevant that you're going at 400 miles an hour. And so that's kind of the idea here. But having said that, this velocity that we apply here, which is a vector, so I won't underline it, this is relative to the static. So this is static. That's very important. And it's relative static because you see this is Newton's second law. And Newton is in the reference frame of the planet. Everything that we drop on the planet responds to the gravity field on the planet. So that's basically why. And so that means that we can also write this statement, if we want, as substituting this value in here, and we can write it as velocity of the control volume or control surface plus W times mass flow rate. And so if you want, these are the absolute forms that you need to understand and understand the reasons for it. So it's quite important that this is the way it is. And you can always reduce this from the way it is, but sometimes you don't get sensible results if you don't use that. So the other things that we talked about, just so we have everything in one place, is the signs of these. And so for mass flow rates, we talked about the sign convention. So positive is coming out. Negative is going in. And we also talked about the velocities that we use in the product of V m dot, this term here. These are always Cartesian. So these are positive in the x direction, positive in the z direction, and negative otherwise. So this one would be positive, but this one also would be positive, right? So V1 is in the x direction, positive x direction, V2 is also in the positive x direction, and likewise. And also the forces are vectoral quantities as well. So in other words, this, and this are all in coordinate directions. These ones are relative to the in or out. So you have to remember. Okay, so that's probably enough in terms of what we'll deal with. So that's the idea. So the first one. So let's talk about static. So in other words, what might you want to know for the jet lev? You'd want to size a motor to it, so you want to know what volume or rate of water you'd want to come out of it. So if you're designing it, you'd want to be able to do that. And so the system is basically this, with a backpack on and a weight of this whole thing. And so I'm going to idealize it just as a box. So this box will be the components that we have. So acting down, you have Wg, weight of the thing times gravity. Going into the system, we have the fluid that comes in from the umbilical. And so let's call this, I'm not sure what I've called it on my diagram, V1 and A1. Obviously an area is this. And squirting out of the bottom is V2 A2. And I suppose in addition to that, we could imagine that we have acting on this control volume a force or forces which are equal to P2, same A2. And we could also have forces acting on this, as you saw. So these aren't detached from the volume, but these are. So that's the system that we have. And so what we could do is we can resolve that. We're only interested in the vertical direction because that's what we have to push against. We're keeping it static, so it's not moving. So we can write this expression that we have here in terms of this, right? Equals VCS plus W times mass flow rate. So what do we have going on here? Clearly, V1, we know from conservation of mass that V1A1 has to equal to V2 A2. That's just conservation of mass. That's this expression where it's steady state, just summing those. So we know that. So if we knew, for instance, this value of velocity, we would get that. I'm not sure that we actually need that. But let's expand these. So what are the forces in the x direction? Well, let's have a coordinate system. So minus WG plus P2A2. Those are the forces that are acting. We don't care about this. This has no component in the x direction, z direction rather. So that's this left-hand side of this. Velocity of control surface, we just said it's going equal to 0. And so we're only interested in the velocities coming out of the system. So the velocities coming out of the system is this velocity here. So it would be V2. It's in the negative direction. And the mass flow rate is in terms of V2 A2 rho. So that this term here is the mass flow rate, and this is this. And so we can start simplifying these. This V2 is coming out of here, so this is a positive V2. Where are we at? This is coming into the atmosphere, so as the jet comes out of the pack, out of the jet, clearly it's in the atmosphere, so this has to be, we could surmise that this is 0. And we have minus, I should call this m, right? Mass, because it's mass times g. W is the product of those. Let's call it mass times g. So we have a minus here and a minus here. So let's get rid of those. And I know the answer to this already. I can just write it as m is equal to V2 squared. Actually, let's not write it as that. Let's write it as exactly that. V2 A2 rho divided by g. And so you know your mass, I don't know, what a person is 100 kilograms, right? This is not a negative, this is just a nothing. So you immediately now we know how to size things. I've written it this way specifically because this represents the mass flow rate. So if you want to be able to lift a big body, you could either increase the velocity it comes out, you could increase the area over which it comes out, or you could increase the density of the fluid. Flow mercury instead of water, or flow water instead of air, right? If it's air, you'd have to have, it'd be a factor of 1,000 difference. Or you could do it on a different planet. You could do it on the moon, and it'd be much easier for you to do it on the moon. And so those are the things you do. So the notable thing, which you don't see if you write it this way, is that these two terms, velocity squared, are included in this. And those mean that if you double the velocity, you quadruple the lifting capacity. If you increase the area or the density, then you only increase it by a factor of 1. But potentially the velocity has a big term. And of course that kind of says something like the v squared over 2g term in Bernoulli that we use to calculate the force applied to the truck from the jet engine. It says that the force that comes from the jet engine is proportional to v squared. And we'll talk about that. So that's simply all we're doing. So it's just a matter of drawing your control volume in the right way. And of course the control volume for this would just be the area around the person, including the incoming jets and the outgoing jets. And so that would be what would come out of it. So these have no part in the pressure. They have a part in the flow, but of course the flow on this other term, there would be another term on here. It would be velocity 1 times the mass flow rate. But velocity 1 is orthogonal to this, so it has no component in the x direction. So the component of this in the x direction is equal to 0. So velocity 1 in the x direction is 0. So that doesn't come into play. That's it. So it's very, quite somewhat straightforward. So that's the static one. The vane is the next. So that's this idea of the Pelton wheel that we looked at. And so it gets a bit more complicated. So 2 is the vane, which is moving but non-deforming. And so this would be the float on top of the water in the bucket that rose to the top when we talked about it last time. And so let me draw this vane the right way. So the vane is the idea is this. We have a vane. This is the Pelton wheel. Let me draw it as the full thing. And what we're going to do is we'll draw a control volume around this. Not too bad, huh? I'm going to put this thing on wheels so it can run on a surface. I'm going to look at the same things that we had before. This is, what did I have? Yeah. So this is W1 in the x direction times A1. So this would be W1 in the x direction. This would be A1 here. I guess I should have given myself some space. This is going to be W2, but in the z direction. And it's going to be A2 on this surface. I should have let myself some more space. We're going to apply a force against this truck, the vane. A reaction, I guess perhaps call it a reaction rather than a force. And what else am I going to do? Yeah, okay. And I'm going to make sure that we understand that these forces are defined. I stupidly didn't use the space, but this is going to be velocity of the control surface plus W, and these together are going to be V static. So the same idea as if I scoot up here as this, that we can, or I guess I didn't mean to do that, that these two vectors do this. That's all that we're doing. Oh, holy smoke. Didn't mean to do that either. I don't know what. Yeah, fine. So oh, that's where it's gone. So maybe I can do this. Perfect. Almost know what I'm doing, you'd think. So, what do we want to do? All right. So we know that conservation of mass, it's steady. And so it's steady. We know that we can use the conservation equation. We'll lose these terms, right, if it's steady state. So sum of in minus out equals no change. So sum of mass in equals 0. So this requires that W1 A1 rho is equal plus W2 A2 rho equals 0. This is out. This is the magnitude of velocity in the z direction, but it's still across a boundary, right? So it doesn't matter that it's in the z direction, because we're not resolving in directions, we're just resolving in or out. So this would be positive, so I won't mark that. And of course, this is going in, it's going against the normal, so this one would be negative. So it balances. So in other words, if we look at those two components, densities don't change, and so we just have that these balance. So the point is that this is equal to 0. So now, when we take this expression here, so let's write that out. sum of forces in the x direction, which we'd like to resolve for, are equal to the velocity of the control surface plus velocities in or out times mass flow rates. Then we can certainly resolve all our forces in the x direction, but we know that the sum of these velocities, the sum of these flow rates are zero because we satisfy continuity. So if it's steady state, so in other words, this is steady state, then mass rate in equals mass rate out. If that is true, then this is the case. And so if this is equal to zero here, then clearly it's equal to here, but this is just a constant, right? The control surface here is moving at some rate VCS, right? This is the rate at which the vane potentially is moving. And so this is a constant multiplied by zero. So the point is that we lose this term. So this term disappears. Not because it is zero, but because this is zero. Okay? And so then it just makes it a bit easier for us to be able to reconcile the case. So in other words, that is always the case. So in other words, for this expression, the force in the x direction is going to be minus Rx equals W1 times the mass flow rate, which is going to be W1 rho A1. What are the signs on this? This is volume in versus volume out. It's going in, so this is negative. This will be positive because it's in the positive Cartesian directions. And then we have to deal with the other one. The mass flow rate equal to W. The component of W in that direction is de facto zero, so we don't have to worry about it. And so the force that we have to apply in this particular case is equal to zero. Okay, well, that's added in there. So we would have this velocity W2z multiplied by W2 A2 rho. So I've written these around. This has no component in the direction we're looking at, and therefore this would be equal to zero. And therefore, we can calculate the magnitude of this system. And so in other words, we know what this force is. We can calculate it because we know the velocity across it is just equal to whatever this velocity is and the area, and we can come up with the magnitude of the force that's applied. So the other thing that we can do is if we come back to this and look at this main equation, let me rewrite it in its full form. Minus Rx is equal to the velocity of the control surface plus W times the mass flow rate. Then the other way, if we want this term equal to be zero, so there's two conditions. The first condition is velocity of the control surface is zero, and that gives Rx is the maximum. That's what we've calculated here. It's equal to the square of the velocity times the density times the area. The second condition that we can look at is the force that's applied goes to zero. So in other words, instead of holding it here by this force, we allow it to move under its own free will. Just like in the movie we watched, it spins around, so it's resisting it minimally. And so if that's the case, then the control surface velocity will be the largest. And so the only way we can get that to be the case if we want this term to be zero, the only term that we can get that to be the case is by these individually being the negative of each other. And of course, these are vectors, so they're not velocities. So in other words, if the velocity of the control surface, I guess we can still get rid of it as equal to 0. Not because it's 0, but because of the product of mass flow rate, and this is 0. Then this can only be 0 if the relative to the boundary velocity is equal to 0. And so what that means is that there's no fluid coming across here because the vane's moving at exactly the same speed, the control surface is moving at exactly the same speed as the incoming fluid. And so these two conditions are, I guess you could draw them out here in terms of this. If it's fixed, then it's not moving, then this fluid is coming in at W1, it's going off here, it's orthogonal to it so it doesn't have an effect, and the maximum magnitude of the force that you have to apply, the reaction, is given by this first equation, just by these terms here. And so this is this particular case, number 1. And the corollary to that is that if this is moving, then this vane is moving at the rate W, which is equal to the velocity of the control surface. Which means that the water which is coming here in at W1 is coming at the same rate at which the control surface is moving, so it never hits it. Or it's just hitting it and pushing it in front of it like a snowplow. And so this is the second condition. So the two end-member behaviors you have are that you either hold it static, in which if you hold it static, you have to resist it with the maximum force, just like the truck at San Francisco International that we calculated with Bernoulli, changing from the pressure being equal to V squared over 2G, or the pressure head being equal to that. That's essentially this expression here. Or you allow the truck to move at the same velocity of the air behind it, never catches up, and so the force that's applied on this is 0, it's not resisting it at all, and it's traveling at the same speed. So those are the two end-member conditions. And if you want to be somewhere in between these, then say that you apply a force reaction which is half, then you'll slow it down because it'll be partway between it. And the importance of that, I guess, or not I guess, is this. If you plot, for instance, the reaction versus the velocity of the control surface, how fast this is going. And so remember what our velocity of the control surface was just what we said, VCS. Then if you look at holding it static, this case, then the force that we apply is going to be a maximum. So we're here. If you allow it to move at the velocity of the control surface, then the force we apply, this reaction, because it's freely moving, is equal to 0. So that's this point here. And it's not a straight line between them, but you could imagine drawing them a straight line. And so the importance of this is that if we look at power that you get from a system, power you can think of the rate of change of doing work, and work is equal to, I guess, W, which is equal to rate of change of Newton meters, right? That's work. So Newton meters power is equal to Newton meters per second, which are equal to joules, right? That's the instrument of power. That's not the instrument of power, that's the measure of power. So power, written quite straightforwardly, is just the product of the velocity of the control surface multiplied by the reaction, or force. I'm going to write it as force just because it's more general, right? So force is in newtons, this is in meters per second, so it's Newton meters per second, so it's power, rate of doing work. And so you see that this product here, if we draw power, which is just equal to force times velocity of the control surface. Well, the force is a big number, but the velocity of the control surface is 0, so this will give us this. The velocity of the control surface is is finite, but the force is 0, so this would give us this. But in between here, at this midpoint, we'd end up with some curve, kind of a parabola. And so the point is that this point is where you're pushing back against it slightly. So in other words, there's some resistance in the generator against being turned, and that resistance multiplied by the velocity at which the generator coil is turning is what's giving you the work that you're converting into electricity, etc. So that's kind of the basic idea. So that's why it's important to be able to understand this idea of the relative velocities in these systems. So that's it. So we have, so that's the reason. So there's two end-member behaviors. One at which you're squirting something, it's held rigidly, you get the maximum force out of it, and that maximum force is given by this resolution of the control volumes and would come down to this magnitude. If you release it and allow it to go without any friction, so it's going at some equilibrium control velocity speed, then that control velocity speed, if the reaction is 0, can only be equal to this relative velocity being 0. And this relative velocity can only be 0 is if the rate of fluid entering into this control volume is equal to 0, because it makes this term 0. And that is only met is if the first hit of this carries the trolley in front of you, and it's forever trying to catch up with a endless stream of water behind you, trying to catch up. Can't catch up because you're going at the same speed. Okay? I think that's the conceptual thing to have out of this. So hopefully that makes sense anyway. But it's an important concept. And so the third one is the decapitated cylinder. And so this is a moving frame of reference, obviously. It's not really deforming because it's not getting smaller, but I guess you could imagine it could be a balloon as well, the same kind of behavior. And so how do we do that? So 3 would be moving, maybe deforming. I guess if the cylinder was getting smaller, it would be, but not really. And so again, that's kind of the similar argument as before. And so, yeah, fine. So this is the cylinder. This is the head that's on it. This is point 1. This is V2 coming out of the cylinder. It's sitting on runners. It has a reaction applied on it. And we define a coordinate system. And so we made the point before that we have to include this term that includes these components. It's very important for this unsteady one that we include both of these terms. When we include these terms for steady state, so steady state is water into the vein, water out of the vein, and therefore this term sets to 0 because the product of a constant here multiplied by a mass flow rate that sums to 0 has to be 0, so that's why it drops out. But this gas cylinder case is not steady state. It can't run forever. There's no resupply of gas into the system. It's kicking it out at one end, so the pressure has to be dropping. You know that has to be the case. It can't run forever as a perpetual machine. And so that's one thing we need to do. Okay, so what can you do? So we can write Bernoulli. And you know where this is going. We can decide on the parts that we know. So certainly 1 and 2, I guess this would be point 2 here. Certainly 1 and 2 are on the same elevation. So this and this would be the same. Clearly, we have a velocity coming out. If it's inside the cylinder and it's a big reservoir, then this velocity is equal to 0. This pressure presumably is not equal to 0. We know that they're dangerous. And once it comes out into the atmosphere, because in the atmosphere all pressures in all directions have to be the same, then this has to be atmospheric pressure. And so we're just left with two expressions. So I guess we're left with P1 over unit weight is equal to V2 squared over 2G. The only unknown is this, presumably, right? If we know what the gas cylinder is. And so we can get the magnitude of the velocity coming out of here. So we can draw maybe a control volume around this. And that's really what we're doing here. That's in any way we please. And we can write sum of forces in the x direction are equal to the sum of velocity of the control surface plus W multiplied by mass flow rate. There is only going to be one component in this particular case, right? I guess this would be the velocity of the control surface that we'd have. We can choose it to be anything we want. This mass flow rate would be equal to V2 A2 times rho. V2 is really the velocity that's coming out of here that we're interested in. So this is really, I suppose it's really a W, right, in some respects, but you can think of it either way. It would be the same velocity that you have here. And we can work with this to figure out what it is. So again, condition 1, we want Rx to be the maximum. So if Rx is the maximum, you could surmise that control surface volume is 0. If the control surface volume is 0, then this is 0. And in other words, the reaction in the x direction, which is positive, is equal to W. So W A2 rho. This would be 2's, right? These are relative to the cylinder, which would be the same as V2. And so what's the sign convention? This W2 is positive, right? Because it's coming out. And this W2 is positive because it's in the positive x direction. And so the Rx would just be equal to what we'd call V2 squared A2 rho. And that would be maximum. And that's done by assuming that this term here is equal to 0. The opposite case for that is where we want the velocity of the control surface to be a maximum. That is going to be when the reaction to it is equal to 0. We're just letting it go free. And so we can go back in here and do that. Well, how do we do that? We know that from this, we want this to be 0. So we can use the same expression. This term now, let me do it in green so you can see the difference. So now we want this term to be, okay, let's rewrite it. So we have Rx is equal to velocity of the control surface plus W, yeah, this makes it a bit more obvious, times mass flow rate. We can still use this mass flow rate to define this. So this is not 0, it's finite. We want this to be 0, and the only way we can do that is if the system reboots next to me. The only way we can do that is that these are equal to each other. So velocity of the control surface is equal to W, or equal to minus W. I should write it out properly. ECS minus W is equal to 0. These are vector components. So if V2 is in this direction, VCS is in the opposite direction. So they cancel out. So in other words, V2 is coming out here. I guess this is not V2. And this is VCS. And so it's exactly the same as before. If you release it, then the velocity comes out of here. It comes out so that it moves this at exactly this velocity. And so if you imagine dropping a brick out of a car as you're going along, then this gas that's coming out, or water, I guess would be gas, is exactly staying static as the cylinder moves away from it. So it'd be leaving a trail, just like a contrail in the sky, and the part that's discharged from each instant is going to stick there, and then the control volume is going to move away from it. So I'll just leave a stream of this that's moving. So this is the key thing. So that's all it is. So we need to be able to define the behaviors in terms of these conditions. And we can imagine that these two end-member behaviors are the same as before. The maximum resistance reaction we have to have is when we're holding it static, in which case the control volume is going at zero velocity. The minimum reaction we have is when it's moving at the velocity, the control surface is moving at V1 in this particular case, V2 I guess in this particular case. And in each of these two cases, it turns out that the amount of work that's done, useful work, is zero, but somewhere in between there's a little bit of reaction required and it's still moving at some velocity, so the product of these is no longer zero to get this, and you end up with a maximum. And you could work out exactly what this curve would look like if you felt so inclined. So that's kind of it. So I'll reiterate back to the beginning is that to be able to solve these problems, we just have to be able to use these equations in some useful way. The important message from today, I guess, is that the conservation of mass equation that we have here is always written in terms of the components. For a steady problem, this term is always equal to zero and is written in relative to the velocity that's coming across the control surface. That's key. The linear momentum equation is written in the same way. This is the same conservation of mass equation. Has to be written in terms of things coming across the boundary of the control surface, always. We have to use the right sign convention that mass rate out is positive and mass rate in is negative. But this term, which is really Newton's second law, this is in terms of the coordinate system. This is always positive in the positive x direction, positive in the positive z direction, and we have to resolve it in those directions. So if we want to write this static velocity, static because it's controlling Newton's law, then we can write it in terms of this vector sum. I guess it is not a vector product, but a vector sum, where this static velocity Vx is equal to the sum of these two components. And for the case of a static system, it doesn't matter because this term is going to go to be zero, and we don't care about it. For a moving system, this term disappears not because we're going at zero velocity, but because multiplying a constant by something that sums to zero is zero, so it drops out. And for the unusual case in a system which is not steady state, this is not steady state because if you leave it to run for 2 minutes, it'll have no pressure in here. So it's like a balloon that's getting smaller. Gas cylinder can't get smaller, but it can lose its pressure. So there's no source of fluid that's replenishing this velocity going out, so it certainly is not steady, right? It would only be steady if the velocity going out is replenished by some fluid going in. And so in that particular case, you have to keep this extra component because that's the essence of the problem. If you don't keep this component, you get a stupid answer. And the reason is here that the mass flow rate is finite. It's not equal to zero. So multiplying it through by this number doesn't give you a zero that you can drop out in the second of the cases we looked at. So that's it. So hopefully that makes sense. So I think in previous years we've gone through the examples that are in the notes. I think it's useful to be able to explain things in this relatively straightforward way and at least understand this concept here. that if you apply a big reaction, the maximum reaction will occur when you're not moving. The minimum reaction is 0, is when you're moving at the same velocity as the fluid's coming around you. So that's kind of an important concept to understand. And at choosing to provide some kind of reaction between 0 and the maximum limits your control surface velocity and allows you to get work out of the system, which is an important concept in life, I guess, for all the things that we use to generate electricity, for example. Okay, sufficiently confused? I don't know. Yeah, I don't think they're straightforward concepts, but I think the punchline is relatively straightforward, and so it's useful to divide them into those three. Look at previous years. I think last year I did it exactly this way. In previous years I've gone through the examples. They're in the notes that we haven't really gone through here. It's only really this vane example, but the other ones, which were jets and other things, are all explained there. And so if you want to look at those, please do that. Okay, so Friday we'll finish off momentum. We'll talk about rotational momentum, when we have, say, a sprinkler in a garden or a turbine wheel in a hydroelectric plant. It turns out that the hydroelectric plant is a very complicated problem, so we won't bother with that, even though one of your examples in your homework, I know, is that. But we will talk about a sprinkler. And so obviously these are the reality of the Pelton wheel that we looked at today. Okay? Thanks very much.